Hello. Today we will continue to deal with questions of governance towards quality at the level of philosophy of governance towards quality. Last time we got to this table here and discussed the various definitions of quality, of the concept of quality, which exist in the subculture of quality management. The definitions were different, and they were unsatisfactory to one degree or another. So let's get back to the definitions again. From now on we will use this definition. The quality of a product is an objective given, and it is a combination of two factors. The first factor is the complex set of metrologically consistent characteristics of a product that are objectively inherent in it. And the second factor is a measure of correspondence of this very complex set of characteristics of the product, and each of the characteristics, with the tasks of satisfying the user's needs in those conditions of product operation and maintenance offered by life throughout the entire life cycle. If we correlate to what I said earlier, the first complex set that characterizes quality, the first factor, a complex set of metrologically consistent characteristics inherent in the product, these are all particularities. This is the task of some particular parameters of the product that should ensure quality. But the second group, the second factor, this is in general on the theme of fitting into the canon as the best combination of all these particular tasks that ensure the satisfaction of the user's needs, and accordingly the quality of the product in its objective sense. Nevertheless, the user of any product is a generation of the culture in which he grew up, in which he lives, and dealing with the objective characteristics of product quality, he introduces his subjective ideas about it, due to which really high-quality products, in the sense of their consistency in all parameters, with the objective laws of all six groups, can be perceived by the user as a quality product, and he can give preferences to those types of products that are supported by the culture in which he grew up. And these preferences can be formed on the basis of degradational parasitic needs of the user, the formation of these degradational parasitic needs in new generations. This means that it's not enough to produce good quality products at the level of the microeconomy. This means that state politics, politics in the sphere of cultural development, should be such that in new generations such nraviousness and world understanding is formed, where preferences are given to good quality products, and bad quality products that meet degradational parasitic needs of people will not be in demand. Again, this is connected with the paradoxical relation to quality, which is expressed in two sayings. The thing cannot be worn out. This is an objective characteristic that determines the quality of many types of products in a previous culture, because if the thing cannot be worn out, and if at the same time the thing meets ergonomic requirements, that is, it's convenient to use, safe to use, then there is no need to replace it with any analog. And as a result, when such a culture of consumption dominates in society, society exerts a minimal load on the environment. Well, in the other definition of quality, the thing is the latest cry of fashion. If the thing is the latest cry of fashion, the latest cry of fashion was this morning, the next cry of fashion may be tonight, and accordingly the orientation of the broad masses to use quality things in the sense of the thing is the latest cry of fashion, generates that which has received the name affluenza, the burning of the resources of the planet and society in meaningless consumption, which generates the maximum load of civilization on the natural environment, and as a result, generates many problems of a different character, both localized within one settlement and global problems. Therefore, you should always understand that there are two mutually supplementary things. Quality of product in the sense of definition 3.1, and the subjective relation of people towards the objective quality of products. And these two phenomena in a certain culture can be incompatible with each other, and accordingly, generate certain problems for the life of society. Therefore, Fursenko is partly right. A qualified consumer who understands quality as an objective given, being a combination of the two named factors, and these characteristics that determine the quality of products are conditioned by objective laws, A qualified consumer in this sense really needs to be educated. But in order to educate precisely such a qualified consumer, it is necessary that, before becoming a consumer, he must be a qualified creator, who senses and understands the impact on his life, his children, grandchildren, other descendants, close and distant people, by all 6 groups of objective laws which were discussed earlier. All of this is general words. Now let's move on to the concretics of how this kind of thing is implemented in practice in order to make it clear for everyone. Here are 2 photos of steam locomotives. Above is a Soviet steam locomotive, Air Class, and below, this is the American steam locomotive, Yellowstone, a steam locomotive created in the 1930s in the United States, produced until the end of the 40s. It served as a prototype for the largest steam locomotive in the world, Big Boy. Let's take a look at the technical performances. Yellowstone, weight 325 tons, length with tender about 40 meters, thrust 65 tons, and its modification Big Boy had a mass of 543 tons, speed up to 130 kilometers per hour, and more than 6,000 horsepower. And now let's look at the technical performances of the Air Class locomotive. Design speed 55 to 65 kilometers per hour, depending on the year of manufacture. Weight 79 to 85 tons, depending on the modification. Length with tender, in various modifications, 23 meters, around 600 horsepower. The question is, which steam locomotive is better? If you just take the consumer approach, then it's clear that Yellowstone is better. But if you look at both steam locomotives from the standpoint of the table that makes the entire complex set of requirements for quality of product, then a counter question arises: better where? And it turns out that for the railways of the Soviet Union, due to various kinds of historical reasons, the Air-class steam locomotive is better. The fact is that the Air-class steam locomotive in various modifications has an axle load of about 17.5 tons. It can move if the steam pressure reaches 5 atmospheres. Well, for comparison, in order to move the legendary steam locomotive of FD class, steam pressure of 11 atmospheres was required. Steam locomotives of Air class proved to be undemanding under operating conditions, even in wartime, when they were filled with water, let's say from the nearest puddle, and heated with anything. And the Yellowstone steam locomotive is a completely different theme, because on our railways at the time of the Revolution, on most of our railways, the axle load was 15 tons. In Soviet times, by the beginning of the Great Patriotic War, we were engaged in railway reconstruction, so that the permissible axle load would be 20 tons. The war dropped us on many railways to 15 tons. And now we are talking about moving to the standard of 25 tons. This decision was made by the Council of the CIS Railway Administration in 2013, and later to switch to 27 tons per axle. In the USA, from the end of the 1920s, axle loads of up to 27 tons were allowed on railways, and locomotives of the Yellowstone and Big Boy class really had an axle load of 27 tons. Therefore, it turns out that in fact, it was impossible to put Yellowstone on our railways, but in the conditions of the American railways, the locomotive Air class would have been an obvious misconception for the simple reason that in this case they would not have used all the infrastructure capabilities that were created. Therefore, if we again correlate to this table of quality, then this example shows the significance of this cell 1.2, the second column in the first line, requirements conditioned by factors of the external environment and socio-cultural environment. Yes, there are also environmental requirements, but there are also socio-cultural ones. In this case, the development of the railway transport infrastructure dictates the characteristic performance of both the rolling stock and the locomotive fleet. And what is good in one infrastructure is bad in the other for various reasons, either excessive characteristic performances that the infrastructure cannot digest without destruction, or insufficient characteristic performances that do not use the full potential of infrastructures. In Soviet times, already in the 1950s, 4 copies of the P-38 steam locomotive had been built. If you are interested, you can search on YouTube and see what it looked like. Outwardly, of course, it was structurally similar to the Yellowstone. That is, it was a steam locomotive of the mallet system, which had 2 steam engines on each side, which worked on its own group of traction axles. There was another front frame under the boiler. The group of front axles, together with the steam engine, was not rigidly fixed in the frame supporting the boiler as one rear axle group, but rotated in relation to the boiler, providing the steam locomotive with the ability to pass curves and turnouts. But the P-38 was designed on the basis of a 20-ton axle limit. Therefore, it was inferior to both Yellowstone and Big Boy in terms of traction, weight, and other characteristic performances. Therefore, questions of quality are not questions of considering a certain product, its variety, in a certain vacuum, according to its own characteristics. There are always questions that in their full complex set are represented by this very table. Last time, we looked through this table briefly, just to show the consistency of this approach. And now we will deal with it in more detail. The first line, a group of requirements, conditioned by the factors of the external, natural, and socio-cultural environment. This group of requirements covers all the stages of the life cycle. Production, operation. Operation is represented by 2 columns. Satisfaction of the customer's needs through the product as such, and product maintenance, maintaining its functionality in the period of operation, and then disposal and recycling at the end of the operation. The second line, raw materials, or storage of product surplus in the hope that the natural environment will somehow process it. What factors conditioned by the external natural environment and socio-cultural environment can impact the production of products? I showed you an approximate comparison of steam locomotives, but this is not the only example. Because if we consider the whole set of technologies that are used by people in their economic activities, then the whole set of technologies can be divided into 2 classes: nature-dependent technologies and nature-independent technologies. Scientific technological progress leads to the fact that some technologies from the class of nature-dependent technologies can move to the class of nature-independent technologies. For example, sailing. In the past, in the era of the sailing fleet, it was a very highly nature-dependent technology. In modern conditions, it can be considered that in comparison with the era of the sailing fleet, navigation has become a nature-independent technology conditionally, because even today there are cases when huge ships go missing in the ocean. There are several known cases where container ships, about 300 meters long, have gone missing, although in a certain statistical sense, these are nature-independent technologies, since in the conditions in which navigation was carried out in the era of the sailing fleet, this was forbidden. Now, in fact, many things are ignored. The same goes for air travel, because in the early days of aviation, flying was very much dependent on the weather. But as the airplane and the airfield network evolved, weather constraints had less of an impact on air travel. Agriculture is a completely nature-dependent technology. The transition to greenhouse farming, to glasshouse farming, to keeping livestock but not to grazing it in nature, in the vast majority of cases, leads to a decrease in the quality of agricultural products. Therefore, the requirements that must be presented in Cell 1.1, they really exist, but in relation to each type of product, they are peculiar. But nonetheless, they must be taken into account, detected, because production is a key factor without which many types of products do not exist. Next, we turn to Cell 1.2. This is what is conditioned by external environmental factors, but affects the possibility of satisfying needs through products. Last time I mentioned the catastrophe that happened to the British battleship Captain in 1869. In the picture on the right, the artist depicted Captain a few seconds before the start of the catastrophe. That is, the water is all over the upper deck. The oncoming wave is running over the hull, is about to tilt the ship. It will lean to its side and capsize. If you correlate with the table, then the designer of Captain completely focused on cell 3.2, i.e., the designer formed a set of requirements, conditioned directly by the tasks, functions that were assigned to this product, that is, to make a combat ship. But practice showed that in order to perform these functions, the ship was supposed to be compatible with the sea, and Captain turned out to be incompatible with the sea for one simple reason, that its designer completely focused on those requirements that conditioned the possibility of conducting combat operations on calm water. Here is another ship on the left. The Russian Imperial Navy had the cruiser Minin. It began to be built in 1870, but its design was started a little earlier, and they designed it proceeding from the desire of the domestic bureaucracy to be at the world level. If the British designed and built Captain, then we want the same. The drawings of Minin were taken to London for agreement with the designer of Captain, Cooper Coles. The Russian Imperial fleet was saved from a catastrophe by the fact that the Captain sank before the Minin was built. That is, the technical backwardness of Russia in this case played in favor, and it could have happened that the Minin, built as an imitation of the Captain, would have set out into the Atlantic and somewhere there would have disappeared without a trace in a storm, the same way as the Captain. The Captain did not disappear without a trace, only because she was in a squadron. After the construction of Minin began, the Captain perished. It became clear that it was impossible to build such a ship. The project was revised, and the Minin became one of the first long-term constructions in the Russian Imperial Navy. Why am I telling you this again about the Captain and the Minin? I'm saying this because one cannot imitate others, because people in another culture design their technology based on their own considerations. And this first line of requirements, conditioned by the factors of the external natural and socio-cultural environment, objectively exists, and it's such that if one copies something else from someone, then it may turn out to be incompatible with the natural factors and socio-cultural environment in which one intends to operate this technology. Many couch-analysts condemn the Israeli tank Merkava mainly for the high pressure on the ground, and they say it will get stuck tightly in the mud, on swampy terrain, on loose soil, and it can make nothing but problems. You see, Israel designed the Merkava in order to fight in the Sinai Peninsula, in the Middle East, where there is no swampy terrain and loose soil. Therefore, for those conditions, the Merkava is a tank that fully meets the possible conditions of its combat use. Therefore, this group, it exists. But this group also affects the stage of product maintenance during its operation. It affects different types of products in different ways. In some, it affects some types, in the aspect of the impact of the natural environment. But it affects some types of products in the socio-cultural aspect, because technology created in one cultural environment, intended for service in it, may not be suitable for operation in a different cultural environment, for the simple reason that the people who are responsible for its operation have their own opinions about it, which are different from those of the developers, and this can lead to the fact that it will be functionally inoperable. In the old days, Nikita Sergeevich Khrushchev presented Indonesia with the Project 68 BIS Ordzhonikidze cruiser. As a result, several years later, it turned into a barge simply because Indonesia at that time did not have either the maintenance base or the necessary culture to maintain it. Go to cell 1.4. There are many questions here too. These questions are also unique in relation to each type of product. Well, the existence of the problematics connected with cell 1.4 is most clearly manifested in nuclear power. because the long-term operation of the reactor leads to the fact that its structural elements also become radioactive. Uranium energy generates decay products that somehow need to be disposed of. The timing of disposal, the dangers, we in most cases ignore them. Well, for your information, the half-life of plutonium is about 26,000 years. That is, if we develop nuclear power, and even if it works without accidents, then we shift the problems connected with the disposal, recycling of radioactive waste and radioactive elements, out-of-order equipment, onto future descendants. There is the opinion that we don't inherit the land from our ancestors. There is the opinion that we borrow the land from our future offspring. Accordingly, the development of nuclear power, for more than half a century, is not the best ethical action in relation to our offspring, at the same level of technology, understanding of the problematics that historically formed science, primarily physics and chemistry, can provide. In other words, the first group of requirements is really relevant, and it covers all stages of the life cycle of the product. But the concretics are conditioned by precisely those types of products that we are going to produce. Next is the second group of requirements, conditioned by ergonomics. In relation to production, this means that the structure must be technological. That is, if we are talking about tightening nuts, then all the nuts must be accessible either for ordinary spanners or for socket wrenches. And there should be no such nuts for the tightening and loosening of which some kind of special, non-standard device is required, devices that allow them to be screwed. In general, ergonomic requirements cover the production stage. And, of course, they also cover the operational stage. Moreover, they also cover the stage of operation, both in the aspect of satisfying needs and in the aspect of technical maintenance of products during operation. Here is one such example, where ergonomic requirements are not considered. The ship's ventilation system is quite large-sized pipes, and they weigh quite a lot. That is, if the ventilation system weighed less, then the efficient load factor would be less. Once, with this having been realized, the diameter of the ventilation pipes was reduced. And in order for air exchange to be sufficient, and people not to suffocate from the stagnant air inside, the airflow rate in the ventilation system was increased. In general, the experiment was unsuccessful for the simple reason that the personnel became intensely ill under the influence of drafts. Another example of this kind. In Soviet times, a fish factory ship was ordered abroad. The technology was simple. Fishing vessels approached the ship at sea, passed the catch to it, where it was further processed into tinned food, frozen fish, and so on. The prototype had a three-tiered superstructure, which assumed the placement of all personnel in single compartments. Our order is considered that for a Soviet person, it was a luxury to live in a single compartment. Therefore, the designer was asked to remove the third tier of the superstructure and place the crew more tightly. Well, of course, they saved on this business, but the land bureaucrats did not think that if the third tier of the superstructure was removed, the ship's center of gravity would be lower, and its pitching would become sharper. As a result, it turned out that under conditions of a rough sea, the sharp pitch made tins fall from the technological lines on the deck. They crumpled and lost their sailable appearance, due to which the structure of the steamer, with a three-tiered superstructure, was correct. But since the third tier could no longer be delivered, they took up the problem of pitching. The cost of this was more than the savings from getting rid of the third tier of the superstructure. To put it differently, ergonomics is significant. And if this is not some kind of drone, not an automatic machine that functions without the participation of people, then, in order for the requirements for the structure of the product in Cell 3.2 to be really implementable, you must first of all make sure that it's convenient for people to interact with this technology, in some cases to live on it. If you do not provide this, then psychologically tired and physically tired staff will not be able to effectively use this technology, even if its indicators are high enough, and it seems that these indicators provide a high level of quality. This also applies to cell 2.3, ergonomics during maintenance. Well, here are two examples. Minivan VAZ 2120 Nadezhda, already discontinued. Units from Niva, body shell from minibus. There were problems with maintenance. In particular, the filler neck for pouring oil into the engine was located under the hood visor, and without a special funnel, it was impossible to pour oil in there. Why VAZ did not locate the valve cover and the filler neck elsewhere, if not for all cars, then at least for this modification, is an open question. Because it can't be said that this would be a catastrophic increase in the cost of the car. But many car service stations complained that the VAZ 2120 minivan was inconvenient for maintenance. In order to get to something, it was necessary to dismantle a lot more, while the cars of other developers did not have such a problem. The ergonomics of recycling is also present. The third line of the table. Requirements directly conditioned by the tasks, functions, assigned to the product. Yes, this is something that exists at the production level, because if you are able to design technology, but you can't produce it, then there will be problems. Well, again, I gave the most striking example. If you are going to build an aircraft carrier, then you need a building site and water area where it can be brought ready-made or for completion. And the parameters of this building site and water area must be appropriate. If you find yourself in such a situation that there is no building site and water area, then either you will be forced to sacrifice the technical characteristics of the product to the existing places, or you will be forced to build a new shipyard in another place and deploy production in it. Next, cell 3.2. It is highlighted with a fill for the simple reason that for most designers, for most developers of a set of requirements for products in life, in their opinion, only this exists. Everything else either does not exist or seems insignificant in their subjective view, and as a result, various unpleasant things can show up. I've already mentioned steam locomotives of the air class. The steam locomotive of the air class was designed by Vaclav Ivanovich Lopushinsky. Russia and the Soviet Union owe him due to two era-making steam locomotives. The O-class locomotives with 4 driving axles and the air-class locomotive with 5 driving axles, which I showed. But when Lopushinsky designed the steam locomotive of air class, Deputy Minister of Railways L.N. Shukin was against the steam locomotive, since he himself had designed the steam locomotive Sh class. The steam locomotive of the Sh class was designed on the basis of one of the locomotives made by Lopushinsky, but the locomotive Sh class had 4 driving axles and a pair of leading wheels in the front. Due to these structural characteristics, it was inferior in thrust to the steam locomotive of air class. Nonetheless, Shukin promoted it, and since Shukin, abusing the administrative resource, put forward more and more claims against the product of Lopushinsky, locomotive air, before going into mass production, was continuously improved. And the steam locomotive Sh class was also promoted into mass production. However, if the air-class steam locomotive was produced until 1956, when the production of steam locomotives was discontinued, then the Shukin steam locomotive was discontinued already in 1918. Well, one of the reasons is that Sh was inconvenient in maintenance. In particular, in order to pour oil into the bearings of the leading wheels, it was necessary to crawl under the locomotive, or do it in a pit, while the lubricating man was in such a position that if he poured oil, he did not see where and how he was pouring it. As a result, in the event of an overflow of oil, the oil would flow directly onto his face. Therefore, the maintenance of shear in many depots was neglected, and the leading wheels sometimes jammed when the locomotive entered a turn. As a result, the locomotive derailed. That is, the questions of ergonomics of maintenance also arose. Lopushinsky, creating the steam locomotive air, managed to fit into the cannon very well. In other words, this whole table was in some way implemented in this project. In 1915, tests were carried out on steam locomotive air. It was found that in some cases it was inferior to other steam locomotives, in some cases it surpassed them, but if we evaluate in a complex way, then it was the best steam locomotive available in the Russian Empire, and practice, its further operation confirmed this, because at the beginning of the 1920s, if not from the beginning, then from the mid-20s, opinions were expressed that the air-class locomotives were obsolete, that they did not meet modern requirements. But the non-development of the railway infrastructure led to the fact that the air-class locomotive was modified and produced within 45 years, and it became the most mass-produced steam locomotive in the world history, for the simple reason that Lopushinsky managed to fit into the cannon. And actually, during the Great Patriotic War, the transportation in the pre-frontline zone of the convoys of the People's Commissariat of Special Purpose Railways was equipped mainly with air-class steam locomotives and its modification of steam locomotives of Ordzhonikidze class, which in many components and assemblies was identical to air locomotives, although it had its own structural characteristics, in particular, leading wheels, which the air-class locomotives did not have. Well, again, the questions of disposal and recycling into secondary raw materials, conditioned by structural characteristics, were also present. The fourth group of requirements stems from the fact that there is no equipment that would not break, and there are no people who would not commit errors. Therefore, there are many questions related to the prevention of catastrophes with minimizing their consequences, which also cover all stages of the life cycle, because industrial industries at the stage of product creation may be conditioned by its improper structure, which contributes to industrial injuries. The operation of equipment can also be accompanied by all sorts of catastrophes. Maintenance can be accompanied by catastrophes. We have an aircraft-carrying cruiser, Kuznetsov, and over the past 2 years, 2 catastrophic episodes have been connected with it. A floating dock sank under it, and the other day there was a fire. Moreover, since they could not extinguish it within the first 5 minutes, there is reason to believe that the volume of repair and restoration work that needs to be carried out as a result of the fire will be large. There were similar cases in the history of the Russian fleet in the past. The 4th Baltic ship, Poltava, is absent from the lists of the Soviet Navy for the simple reason that there was a fire in its first engine room, the boiler room, and after that it was not put into operation, and it went as a donor to maintain the combat effectiveness of the other 3 battleships of this project. Again, the creation of a submarine fleet in the Russian Empire was accompanied by the fact that a catamaran was built, which was originally called Volkhov. Then it was called Kommuna in Soviet times. In fact, it was a large floating crane, capable of lifting a submarine into the space between 2 structures. Look at it on the internet, it's still in service, it is still in use, but its creation was conditioned precisely by the possibilities of accidents and catastrophes, and the problems associated with Chernobyl and Fukushima could have been somewhat lighter. If, before the construction of the nuclear power plants and the reactors, a line of equipment intended for work after accidents with nuclear reactors would have been worked out and produced. The 5th group of requirements is the requirements conditioned by the technology and organization of the implementation of all stages of the life cycle. Let's take a look at the history of shipbuilding. In the 19th century, there was a transition from the construction of wooden ship hulls to the construction of iron and then steel hulls, How did technology evolve? Several stages can be distinguished. On the slipway, where hulls were assembled, there were sheets brought to the slipway that were riveted to make a hull. The next stage is welding. The initial period, there were sheets brought to the slipway that were welded. But if you are going to design a ship, then you should immediately think about which technology will be used, riveting or welding. In particular, the structure of the welded hull is somewhat lighter than that of the riveted hull, all other things being equal. Further development of technologies. Sections welded in the workshop began to be brought to the slipway. This accelerated the hull assembly process and also required some adaptation of the hull structure to this. And nowadays, ships are built from volumetric sections, in which almost everything that can be installed is installed. And this leads to the fact that the structure of the ship is developed for this technology, and the technological process also splits into two stages. The first stage is the calculation of everything in order to make sections, and then the actual production of sections in workshops with a high energy supply capacity, which greatly improves labor productivity. And a modern cruise liner, after ordering it, is handed to the customer in the course of approximately 3 years. Of these 3 years, 2 years are spent calculating the technological process, and 1 year on construction. The same applies to the features of operation, maintenance, and disposal. There are many things that are conditioned at each of these stages precisely by the technologies and organizations, the implementation of those processes that either make it possible to fulfill the user's requirements to satisfy the needs, or to maintain and dispose of products that are out of service. That is, this table here is the information structure for the implementation of the entire function of governance towards the life cycle of a product. Now back to the entire function of governance. The entire function of governance is a key concept for governing everything, including quality of product in the sense of definition 3.2, and in the sense of implementing the table of the life cycle and distributing product requirements along groups and stages of the life cycle. Therefore, the detection of a factor of the environment which puts pressure on the psyche, and thereby causes the need for governance and setting of objectives in relation to the detected factor. Now we will be engaged in these two stages with more detailedness. We live in a condition where an aircraft carrier is the only means that allows tactical aviation to be carried to any area of the world without coordinating a route with countries of the world that are on the way to this area. If there are no aircraft carriers and you are forced to ensure the flight of an aviation group, it's basing somewhere outside the area of this group. Well, as is clear from this table, if you want to build an aircraft carrier, you must form a set of requirements for its building and implement this set of requirements in the structure of the ship, in the structure of the aircraft that will be based on it, in the infrastructure facilities that will ensure the operation of the aircraft carrier for a long time. That is, the quality of products is set at the level of the set of requirements, first of all. Where do these requirements come from? They come from how we detect a factor of the environment that puts pressure on our psyche and causes the need for governance. Further, our setting of objectives in relation to the detected factor. In fact, there is such an objective law. The quality of products throughout the entire function of governance is a kind of ladder. The maximum of quality is conditioned by the fact that putting forward a set of requirements for products, you fit into the canon. Further, the actual structure of the product is worked out, and the constructionally conditioned level of quality may turn out to be lower than specified in the set of requirements because the developer could not meet all the requirements, or made some constructional mistakes when the requirements seemed to be satisfied, but at the same time, there are side effects that remove specific items from the canon. Next comes the production stage. And at the stage of manufacturing a product, the quality can be dropped lower than it's constructionally possible. Then the product is passed to the consumer, and the consumer in the course of operation violating the rules of mandatory work to maintain the functionality of the product, can drop its quality even lower. Therefore, this ladder from setting of objectives, which is expressed in a set of requirements, through a structure that's oriented on satisfying the set of requirements, further, on the quality of production in accordance with the structure, and maintaining functionality during operation, must also be borne in mind. To put it differently, from the idea to the implementation of use, the quality can fall really low. Therefore, once again, the entire function of governance, at the level of the set of requirements, is realized here, in this very table. And then, constructionally, servicely, it can either be dropped or provided at the level specified in the set of requirements. But it can't be higher than you specified in the set of requirements. In particular, the set of requirements made for Captain manifested itself in a catastrophe. Whatever structures were there, no matter what the ship's manufacturers, the builders did well or badly, everything was killed at the level of the set of requirements. Now let's see what we have, so to speak, in our national path for the development of aircraft-carrying ships as part of the Russian Navy. Well, we won't touch upon the Moskva-class helicopter carriers, since these are very peculiar ships, and in fact not the most successful ones for a number of reasons. And here are the first so-called aircraft-carrying cruisers, Project 1143. The first three vessels are Kiev, Minsk, Novorossiysk. The fourth vessel is Baku initially, then Admiral Gorshkov. And now it is the Indian aircraft carrier Vikramaditya, rebuilt into an aircraft carrier with a ski jump takeoff in Severodvinsk. Let's look at this ship from the standpoint of working out a set of requirements for it. I have such a feeling that this project was born as a result of the aspiration, most likely of Sergei Georgievich Gorshkov, that it would be possible to replace a group of ships at sea with one ship. In essence, this is an attempt to attach an airfield to a missile cruiser. The result was something that caused a certain amazement, both in the Soviet Union and abroad. However, 4 ships were built. If we talk about it as a combat vessel, then it's possible that it made sense as an anti-submarine cruiser helicopter carrier. The photo on the left shows that one helicopter is standing on the runway and several Yak-38 vertical takeoff planes are standing on the right of the runway in the aft part of the flight deck. The existence of vertical takeoff and landing aircraft is astonishing, because in fact an aircraft capable of taking off vertically and landing vertically is a very narrow direction in aviation, which can solve very narrow tactical tasks, because by its flight and tactical characteristics, an aircraft of vertical takeoff and landing loses to most aircraft with normal takeoff and landing. That is, running for takeoff, landing, and running after landing. As a result, Yak-38, the radius of combat use was less than 200 kilometers. There was no onboard radar station in a suspended container, and the total number of these under-aircraft on the ship was less than the total number of normal aircraft on most aircraft carriers in the world of that era. In other words, at the level of putting forward a set of requirements, it is a clear failure. Well, in fact, it became clear that the ideas of Gorshkov, which he promoted from the 1960s to the end of his days, the construction of ships equipped with vertical takeoff and landing aircraft, which would supplant classical aircraft carriers, turned out to be nonsense. And in this nonsense, in the Soviet Union, colossal funds were invested, and no one sane was found who would neutralize Sergei Georgievich. So these ships were abandoned, and something like this appeared. This is Project 1143.5 Kuznetsov ship. The next variant, named 1143.6, is the failed Varyag, which the Chinese bought from Ukraine, towed to China, and put into operation. Now look at the scheme on the flight deck. At the bow, 2 accelerating tracks go to the ski jump. Between them there are 12 silos of heavy anti-ship missiles. Again, an attempt to attach an airfield to a missile cruiser. But anyway, this is already a ship designed for more or less normal aircraft to be camp-based. But a ski jump takeoff is provided, not a catapult one. The reasons are simple. Here is a scheme of a catapult. A steam catapult, cross-section 3. 2 cylinders up to 90 meters long. In essence, this is a steam engine. A slot runs along each cylinder. The catapult is in the process of being assembled. Well, you understand that if this is a steam machine, and there is such a slot, then steam will escape through such a slot. Therefore, there are devices that open the slot before the shuttle passes. This is shown in the scheme, number 5, and these devices close this slot after the shuttle has passed a certain distance. Next, see part number 4. It has a conical shape. And at the end of the catapult there is number 2. This is a hydraulic brake. That is, this cone enters the filled water and stops the shuttle. Moreover, it must stop it also in the case that the plane breaks away from the catapult and all the power goes only into the movement of the shuttle. In other words, ship catapults are very complex devices that are powered by steam not even from a boiler, but from a steam accumulator, a reservoir with superheated water, which turns into steam as soon as the catapult maneuver valve opens, and due to the pressure drop, the water begins to evaporate. Therefore, the desire to get rid of the catapult is quite understandable. But then the next aircraft carrier, 1143.7, appears. Its construction began, but at that time the Soviet Union collapsed, and Russia was unable to finance Ukraine, and Ukraine was also unable, and this aircraft carrier named Ulyanovsk was dismantled on the slipway in the initial stages of the formation of the hull. But also pay attention, it provides a ski jump takeoff, and between the runways before the start of the ski jump, there are also missile silos, 9 rectangles in the picture. And on the left side of the flight deck there are 2 catapults. And on them there are planes of long-range radar detection, or reconnaissance and target designation aircraft. That is, it is a carrier-based AWACS, Airborne Warning and Control System. Such is the national path for the development of aircraft carrier ships in Russia and the Soviet Union. There are many people who think that all this is good, and the fact that we have built aircraft carriers, aircraft carrying cruisers, which can replace a whole group of ships at sea due to the fact that there are missiles, and because they have a ski jump takeoff. They are cheaper than American aircraft carriers. There is quite a large number of adherents to this point of view. Now let's take a comparative look. In the top photos, in the top row on the left, there is an American aircraft carrier of the Nimitz class. On the right, Kuznetsov. A very simple question arises. The architectural type Kuznetsov has existed for more than half a century. The catapult is indeed a very technically complex device, expensive to manufacture, requiring regular maintenance, requiring an increase in the steam output of the ship's boiler room or reactor plant. Why, after seeing Kuznetsov, do the Americans continue to build aircraft carriers with catapult takeoff and do not want to switch to a ski jump takeoff? To answer this question, you need to understand how process thinking differs from discrete thinking. With discrete thinking, we see 2 aircraft carriers, and it seems to us that Kuznetsov is better, due to the fact that it's technically simpler. And accordingly, the Americans are some idiots who can't understand this superiority and continue to build aircraft carriers with catapult takeoff. Now let's look at the same thing from the standpoint of process thinking. The flight deck of an aircraft carrier can be used in 2 modes. Mode 1, striking at the predetermined time. And in this mode, both ships are approximately functionally the same, because everything that's capable of flying rises to the flight deck. The Americans have 2 bow catapults, we have 2 starting positions, or even 3 starting positions, that begin to provide the scrambling of aviation. Things are good. Now let's look at the other mode of using the flight deck. The mode when the time of the strike is unknown. That is, a certain signal or command should be sent to the aircraft carrier, according to which it must urgently scramble an air group of maximum strength to strike. And what happens in the remaining time when the aircraft carrier is ready for this mission, this task? In the remaining time, the deck AWACS should fly and illuminate the situation. The AWACS must be accompanied by fighters. Some kind of duty group must be continuously in the air. But they can't hang in the air forever. This means that when they run out of fuel, they will have to return to the aircraft carrier, and another AWACS and another unit on duty by this time should be up in the air. The situation is precisely shown in the photo on the left. Everything intended for an emergency departure is on the flight deck outside the runway. We see a helicopter on the runway. It's there in case of unsuccessful takeoff or landing. When the pilot catapults, the helicopter has to pick up the pilot, the crew, from the water after the unsuccessful takeoff or landing. Further, on the catapults there are two fighters. One fighter extremely close, the first, is at the aft end, to the left side, and the other fighter behind the helicopter. Further, on the flight deck, on the runway, there are several more aircraft. The AWACS should be there somewhere. By the time the previous AWACS returns, all this will be up in the air. The runway will be free. There is space on the flight deck where the landed aircraft can be placed. It seems that Kuznetsov can work in this mode. Just note that where the Kuznetsov has a ski jump, the Americans have more than 10 planes. And the Americans will never build aircraft carriers with ski jump takeoff, for the simple reason that if an airstrike is necessary on an emergency call, an aircraft carrier with a ski jump takeoff will lose in terms of the number of aircraft to an aircraft carrier with a catapult takeoff. The dimensions of the Nimitz class aircraft carrier: 333 meters long, 78 meters wide. Kuznetsov is slightly smaller, 305 meters long, 72 meters wide. But count the planes that can be placed on the flight deck, and you will see everything. Everything will become clear to you. Below, on the left, is one of the first design versions of the British aircraft carrier, Queen Elizabeth. Back then, several variants were considered, and there was no talk about the theme that the Americans chained the brains of the British concerning the F-35. Queen Elizabeth is actually built without catapults, but with ski jumps for the F-35, which can take off from the ski jump and land vertically. Pay attention to how the catapults are located. In general, although the number of catapults is 2, but not 4 as the Americans have, nonetheless, the location of the catapults also implies the placement on the flight deck of the maximum possible number of aircraft in the flight deck operating mode, ready to strike on emergency call. On the right, at the bottom, there is one of the variants of domestic development taken from the internet, the Storm. Well, first of all, again, a ski jump takeoff, and besides that, 2 islands, like on the Queen Elizabeth. Moreover, the Storm is declared as a nuclear aircraft carrier. Here, Queen Elizabeth has 2 islands for the simple reason that she has 2 engine rooms, and gas ducts are made into 2 pipes, which are placed along the length of the ship, and around them there are 2 islands. Why are there 2 islands? The answer is open. But one must understand that each island, especially of an anti-streamlined shape, creates a vortex trail that goes behind the stern of the ship into the glide path zone. Well, here it turns out that from the point of view of aircraft carrier aerodynamics, 2 islands are always worse than 1, because here there is such a saying: everyone is equal in front of the ramp. This one was shot on one of the American aircraft carriers, apparently in the early 60s. This is a few seconds before the plane crash. The aircraft approaching for landing falls into the area of the aerodynamic shadow behind the stern of the aircraft carrier, and in the near future is going to hit the aft edge of the flight deck, which in naval jargon is called the ramp. Because there is a visor, under it there are lamps that illuminate the flight deck at night, and outwardly it looks almost the same as a ramp on a theatre stage. And here we once again come to the question: what should an aircraft carrier be like? It turns out that a landing on an aircraft carrier is carried out not in the same way as a landing on an airfield. If an airplane lands on a land airfield, it follows the glide path, enters the beginning of the runway, keeps an altitude of several meters above the runway. The stage is called leveling, after which it releases the engine thrust and touches the runway with its wheels, and then it runs on it. This is not the way to land an aircraft carrier. There is no leveling phase. Several arresting gears are stretched across the runway. On the Kuznetsov there are 4, on the Storm there are also 4. And the touchdown point, where ideally the plane should touch the deck with the brake hook and catch on the arresting gear, is located between the second and third arresting gears. So the plane goes along a straight glide path and should be there. Touch the deck with the brake hook between the second and third arresting gears. And in fact, the further this point is from the aft edge, the higher the landing safety standard. Because the situation when the aircraft fails due to the aerodynamics and the ships rolling below the aft edge of the runway, the probability of this event is lower the further the calculated touchdown point is located from the aft edge. Kuznetsov loses about 10 meters in length from the aft edge to the calculated touchdown point to Nimitz. And accordingly, in those conditions in which Nimitz can actually safely carry out, well, let's say, with a certain safety standard, takeoff and landing operations, the smaller in size Kuznetsov will not be able to carry out such operations with the same safety standard. And accordingly, it will either not be able to perform combat missions, or their performance will require a higher level of qualification of the flight personnel, or more advanced landing systems that will ensure the touchdown by the brake hook of the calculated touchdown point in any weather conditions. In other words, whether we like it or not, the Americans are not much mistaken when they release an aircraft carrier from any other tasks except for the task of ensuring takeoff and landing operations and the ability to scramble an air group of maximum strength on an emergency call. But we, for not quite clear reasons, apparently cannot turn away from the national path of development and adherence to a ski jump takeoff. But if we talk about the quality of the ship, then in this case, the quality is lost at the stage of specifying the set of requirements for the ship. That's it for today. Next we will look into how the entire function of governance is implemented in the subsequent stages of the entire life cycle of a product, and how it is expressed in the quality of this product.